is done? You give some potential to this to reduce this N2 plus to N2 to make a radical here on the phenyl ring. So that radical is bonded covalently with the ITO glass substrate because ITO is a semiconductor, so it has free electron on the surface. So if a radical is formed, that is bonded with the ITO surface. Now what happened? So that tarpyridine moiety, the mouth is open outside, and once the other side is bonded to your substrate. So this is called the template ITO, we call it, because you have an anchoring group attached to the substrate. So this is a cyclic voltammetry. It is a technique on which you give potential to your substrate and you see whether oxidation and reduction is happening or not. So the current is flowing in the negative direction, so it is called reductions. That means you are giving electrons. So you see here, first cycle, the very good reduction peak at minus 0.68 volt appears. So which is because of the reduction of the N2 plus to make the radical. Now, on the second cycle onwards, you don't see any kind of reduction peak. Why is such? Because after forming this, all the sites become filled. There is no available site there is no site available for further reduction. So that's why from the next second cycle onwards, you don't get any kind of reduction peak. So we characterize this substrate through XPS, X-ray photoelectron spectroscopy, on which we found the peak of nitrogen, which comes at 397.8 electron volt. Then we design our system. So now we have the tarpyridine open outside. So this is our ligand design. So we smartly designed this ligand. We incorporated nitrogen here. So why we give the nitrogen? To give a 3D feel to the assembly, because triphenyl, I mean, you know the geometry of this molecule. Now imidazolium is added, I told you, because of the counter ion, which will facilitate the charge transfer. Then the iron tarpyridine moiety which is used, iron tarpyridine moiety gives a metal to ligand charge transfer transition at 570 nanometer, which is hugely color. When you will oxidize it, that means when you will convert iron 2 to 3, then that charge transfer is prohibited because already your metal is electron deficient, so it will no more give the electron to the ligand antibonding orbital. So you will see the colorless. So in that way, the previous examples, whatever we saw, that mechanism is actually going on. Now you see, we have the tarpyridine. Then we, in the next slide, we'll see, we have the templated tarpyridine. Then we deep in the ligand solutions, sorry, metal solutions. Now metal is iron perchlorate we use. So the iron is coordinated here and two side solvent molecules attached. Then we wash it, again we dip it and the ligand solution. So now only one tarpyridine will be, because it is a pseudo octahedral geometry. So already iron is coordinated to 3 nitrogen. So other 3 nitrogen of the ligand tarpyridine it will use to make the pseudo octahedral geometry, but still other two are open outside. Now what will happen? So that again you dip in the metal solution followed by washing and ligand solution. So you repeat this process several times to make the assembly. You can see on the right side top, we have monitored the growth, which is you see after each double cycle, I mean 2 cycle, 4 cycle, like one time dip on iron and one time dip of ligand L1, it give you 1 cycle. So 2 cycle, 4 cycle, similarly we just check, you see the gradual increase of the metal to ligand charge transfer at 570 nanometer. It is increasing. That means your assembly is getting thicker and thicker. And this was further characterized by different techniques through charge density, because if you have more iron tarpyridine moiety, you have more redox active center. So you will get more charge on when it will grow continuously. So you see the red one is the charge density. It is from different deposition cycle. It is growing linearly. Similarly, absorbance also going linearly. And thickness through ellipsometry, we check the thickness, whether thickness is also increasing or not. And you can see the blue one, which is also growing linearly. So in this way, we monitored the growth. Then we characterize whatever assembly is formed. You need to know what is there. Now we characterize, and through cyclic voltammetry, whatever I told, you see here, we are giving the potential in positive directions, because I mean in cyclic voltammetry, it is a technique, you scan it in a different potential window. Now you see at 1.220, The iron 2 is oxidized because this is anodic peak potential, this is cathodic peak potential. Anodic peak means oxidation, cathodic peak means reduction peak. Now it is getting oxidized at 1.220, then it is coming back, all iron get oxidized, then again you are reversing the voltage. So the reduction happening, so you get a reversible peak. This is called reversible peak. So, and the peak difference, the daily is 1 millivolt. So this for a surface confined system, it's actually the peak to peak difference should be 0. So we are getting nearly 1 millivolt. So which indicates that our assembly is surface confined. Then through XPS, we found the iron 2p3y2 and different terms we found on through XPS. We got the peak of iron as well as nitrogen, and two kind of nitrogen, because imidazolium has the positive nitrogen and tarpyridine has the neutral nitrogen. That's why we got two different peaks. Then through same the scanning electron microscopy, we saw the structure. We can see at 200 nanometer height. You see there is a branch structure which is forming on the on the surface. So in this way, we characterize our surface. Then we fabricate the device. So what is there? We make a four layer device where you have a first ITO surface, then you have your electrochromic material, that is our iron tarpyridine, whatever I show you the geometry of this. Then after that, we use a gel electrolyte. Why we need gel electrolyte? Because another I'll tell you another counter electrode we use, that is another item which is blank one, because positive negative is there to complete the circuit. Now if you will not use any mediator, then it will just the short circuit will happen. That's why gel electrolyte is used to avoid that short circuit, and it will conduct the charge between one electrode to the other. So you see here, just a minute. Hello. Yeah. Seriously. Okay, so can you see my slides? I have only two slides. So I got the reminder. Can you can my screen is visible?
Yes,
Okay, okay,
yes.
okay, okay. Okay. So only two slides I have. So don't worry, I'll finish in time. So you see here, so that device you can see on the right side, the transmittance. We got a 40% transmittance chance. So when you give plus 3.2 volt voltage, then it become oxidized, all iron to become iron 3, and you can see the colorless device you can get. Now you reverse it, minus 2 volt energy you give, then all the iron 3 become iron 2, and the MLCT again started occurring, and you get a blue color device. We also patterned it, and two type of device we made. One is pattern device, one is printed device, where you can see we wrote our lab OSML, organometallic and smart material laboratory. So here this kind of color to colorless transitions, you can write it also. So this means, and I have given a video here. I think you can see it. And you see here the on the top side, there is a color change timing I have seen here for 95% conversion from this is colorless to color. It taking 0.49 second, and for color to colorless, it is taking 0.90 second, which is less than second. And it is quite stable up to 4,500 cycle, and there is only 10 to 15% performance losses observed after such cycle. So you can see the video. I think you can see it. So in one side, left side, there is a color to colorless transition is happening. And here OSML, the transition you can see here. Okay, then let's summarize it. So we synthesize a novel imidazolium linked moiety and means iron tarpyridine based moiety, which we used for the assembly formation on the ITO substrate. Then that designing gave us a fast electron transfer, which leads towards the switching, means fast switching. Also, we got a coloration efficiency of 275 centimeters square per coulomb, which is comparable to the recent trend, and also a moderate operating voltage between 3.2 volt to minus 2 volt. optical contrast of 40% and cyclic stability up to 4,500 cycle. So these are my few publications. In early 2020, we published on this on ChemCom. Then recently on hazardous material, we published of dichromate capture. What were the bulk application we had? Organizers for again inviting me. My supervisor, Dr. Jayanta Chaudhary, CSR for my fellowship, CIF IISER Bhopal for the instrumentation facility, IIT Kanpur for XPS, and DHT Government of India for the project funding. And thank you all. This is our Utkal community at IISER Bhopal. We had a small family, Odia family here. Thank you so much. I'll happy to have some questions.
Thank you, sir, for your impactful and knowledgeable presentation. Has let us our deeper understanding on the concerned topic, ultra-modern smart materials, a fast-switching electrochromic device. I am extremely thankful, sir. Now it is the time of vote of thanks. I would like to request Ms. Snehasini Devagoswamy, Assistant Professor of Chemistry, Ramana Degree College, to propose vote of thanks.
Thank you, sir. A very good evening to all. Honorable speakers, distinguished respected principal ma'am, and dear participants. On behalf of Chemistry Department, Ramana Degree College, its entire fraternity, I feel immense pleasure to propose the vote of thanks. I would like to thank our chief speaker, Professor Dr. Sabita Dixit, Maulana Azad National Institute of Technology, Bhopal, who honored this webinar with innovative thoughts. I thank to another speaker, Mr. Satyaranjan Jena from IISER Bhopal. We are really enlightened with your knowledge and presence. I would like to thank our beloved principal ma'am for cooperation and support in every sphere. I would like to thank to all staff members of our college, students and technical supporters, and our valuable participants for their unceasing support and coordination for making this webinar as a grand success. Once again, I thank one and all. Thank you.
Thank you, Sabita ma'am. Thank you, Satya sir. Thank you, Principal madam. Now the session is over.
Thank you, thank you. Namaskar, ma'am.
Namaste.
Namaskar.
Namaste, ma'am.